Logic gates and combination circuits. In this presentation, we're going to be looking at how we can create logic gate equivalent circuits for standard push button and relay operation. Now, long ago, the world ran on relay logic alone. There were no digital controllers or PLCs to accomplish the tasks. As the digital world expanded, it started to replace relays in large, complex manufacturing processes. This meant basic pilot devices in the field would need to be rewired from relays to digital controllers, like logic gates. Now, relay logic requires pilot devices to be wired in specific configurations to each other in the relay and the contact in order to achieve a specific operation. So this one here, we have two push buttons, they operate the coil of a relay, contact closes, and a light turns on. Digital logic requires pilot devices to be wired directly to the controller regardless of the operation. A different digital controller would then be chosen for each specific operation. So there's my AND gate, which is really just, well, 3 resistors, a source, and 2 transistors wired in series, and I can get the same operation. So it's a much different method of wiring pilot devices back. Now, relay and digital logic systems complete the same sequence of logical operation. Digital logic systems have the advantage over relay logic because, well, they're smaller, less space required, less power consumption, easier to change the operation, easier to troubleshoot, no moving parts, and more flexibility of controlled operation. Now, to convert the relay logic to a digital logic system, we need to go through a few steps. So we're going to break that down for the first one here. So the steps are, first, consider when the push button will provide a high signal or a low signal to the relay coil. Sketch a truth table for the push button signal and the load. And finally, determine which logic gate aligns with the truth table sketched. So there's my truth table, and I'm going to say, well, looks like I got 2 lows and, well, the coil is not energized, therefore the light is not on. What if I push down 1? Well, then if I push down A, I get a high, the coil turns on, and the contact closes, and Y, the light comes on. Okay, what if I instead push down push button B? I get a high off push button B, and the coil's energized, contact closes, the light's on. What if I push them both down? Well, same thing, coil's energized, contact closes, and Y, the light is on. Okay, well, that kind of makes sense. I get a truth table now. That truth table aligns with an OR gate. A plus B equals Y would be the expression. So a standard OR gate with 2 push buttons wired into the inputs and the light wired onto the output would replace the relay. So the relay and its associated contact would no longer be required. Now, it's important to understand that changing the pilot device normal state would not change the logic gate required. And that's because you would end up with exactly the same truth table. The truth table would still be, if this is high, coil's energized, contact closed, light is on. Same with this one if it's high. It's just, well, you're not pushing them down, which is fine. So you'd still end up with an OR gate. Now let's take a look at a separate one. This one has 2 push buttons in series. So if there are 2 push buttons in series, you could go through the truth table and work out that, well, the relay coil's only coming on when both A and B are pushed down or sending a signal of 1. So if you put both those push buttons on A and B, right, then it would be an AND gate, and again, the AND gate would replace the relay and the contact. What about this one? A little bit different. We can see there's only one pilot device, and that should be a little bit of a hint to you. If there's only one pilot device and one input signal, this kind of needs to be a NOT gate. And we can see here, when this is not being pushed, or when this is not being pushed, I've got a high signal, this is on, closed, and Y is on. So we'd have A is equal to Y. What about this one? I've got the A, the B, but notice I have a normally closed contact. A normally closed contact means that right now the light is on, but there is no signal coming from A or B. So what that means is that now we have a NOR gate. So when I have a normally closed contact, that normally closed contact should elicit for us an understanding that there should be an inversion on the output of my logic gate. And just follow through the operation. If I push down A, what will happen? Coil will energize, contact will open, light will turn off. And that's exactly what's taking place here. The demorganized equivalent would also be correct, and that would be a negative and. And that would be having two negations, right? Inverting on the inputs of A and B, but nothing on the output. What about this one? Two push buttons in series and a normally closed contact. Well, this one is going to use a NAND. And that's again because I have a normally closed contact on my relay. And right now, the coil is de-energized, the contact's closed, and the light is on. As soon as I push down A and B, the coil will energize, the contact will open, and the light will turn off. So this Boolean expression for the NAND gate would be true, as well as the demorganized equivalent, which would be a negative OR gate. What about this one? And this is getting pretty outlandish. I've got 4 normally open push buttons. Think about it for a few moments. What would this look like as a logic gate equivalent? I'll give you a hint. It's actually going to require more than one logic gate. You could say that this chunk here would be, I don't know, maybe A or B could be pressed. And this one over here, C or D, could be pressed. But then if you look at this bank and this bank, you could say, well, maybe this one of these could be pressed or one of those could be pressed. So you really need to break it down and consider what the implications are of that. So really, I've got 2 OR gates, one for the A and B and one for the C and D. But in order for the coil to be energized, I need at least one of these to be on and one of these to be on. And the operative word is and. The and is this line in between here that connects both those banks. So really, I need an AND gate. So there is 3 logic gates in this system in order to replace the coil and the contact of the relay that we see here. The light would connect here. So this would be A plus B and C plus D. So A or B and C or D. Finally, what if we were to add a normally closed contact here? Well, a normally closed contact simply affects the output. And so just like we were saying before, what we would do is add an inverting circle or dot to the output of this logic gate connection. And because it's on the output, we would have a line representing over top of each one, well, a solid line going over all of the inputs. And that's how you tackle combination circuits with a logic gate system.